Hi everyone. In this video, we are finally ready to start actually solving linear systems of equations. I hope by now that you've had a chance to review what a system of equations is and how we use matrices as a powerful tool to help us work with linear systems of equations. With that background in mind, now we can actually get to the task at hand, which is that we would like to actually solve for the unknowns in a linear system of equations. Remember that some linear systems are inconsistent and don't have any solutions whatsoever, right? So when I say we are hoping to learn how to solve linear systems, I should add, if possible, right? It's not always possible. To help us do this, I'm going to start off with sort of three observations, three remarks just about solving linear systems in general, and I'm going to write them on the board behind me. By the way, the title of this is EROs and REFs, which are, of course, abbreviations for something, and I'll point that out as we go through this video. Okay, so let's make three remarks to kind of get started with this. These are three remarks about linear systems of equations, and in particular, solving linear systems of equations. So the first one is that a linear system is easy to solve. A linear system is easy to solve by something that is usually called back substitution. It's easy to solve by back substitution if it is in what is called a triangular form. Okay, I kind of need to explain what I mean by that. I think an example will pretty nicely make my point here. Let me write down a linear system of equations. Suppose I had 2x minus 3y plus z equals 6. And then suppose my second equation was 4y minus z equals 8. And finally, my third equation is z equals 4. So this is my linear system of equations, and the goal is to solve for x, y, and z. Now, you probably are looking at it and thinking, I could find a way to do that. Starting from the bottom equation, we know what z is equal to, and we can use that value in the middle equation. Plugging in the value of z allows me to then solve for y. And once I know what both y and z are, well, then I can take the first equation and solve it for x, right? Why does that work so nicely? It's because the system is in this, what I call triangular form. It almost looks like a triangle on the left side, yeah? The last equation only has z in it. The equation before that only has y in it. And the equation before that, y and z in it. And the equation before that has all three variables in it. But I can kind of work from the bottom up to the top. So if I know that z is equal to 4, and I plug that in over here, you can very quickly solve for y. It turns out that y is equal to 3, right? So if I solve for y in this equation and plug in 4 for z, I will get y equals 3. And then if I work backwards even further, and I plug in y equals 3 and z equals 4 into the first equation, I will let you guys check it out that we can actually solve for x. It turns out to be 11 over 2. Okay? So this is solving a linear system by back substitution. And what is the solution? I would like to get into a good habit of writing down my solution as a set of points. So I'm going to use braces. I'm going to want everybody to do it this way, using some braces around our solution. And in this case, we just put the coordinates of x, y, and z into those parentheses. Here is our solution right here. There's, in this case, just one solution to the linear system. Okay, So that is the first observation. We can solve a linear system easily by back substitution if it kind of has this triangular form that I've showed in this example. Okay, let's get to the second observation, the second remark here. No solutions to the system. No solutions to the system are gained or lost. We don't gain anything and we don't lose anything, right? If we perform these operations. Let me tell you what I mean. If we perform these operations. So what operations am I talking about? Let me come back up to the top here. Give myself a little more room. There are 3 of them. There are 3 operations here that I'm talking about. So let's label them as maybe A, B, and C. So the first one, right? The first operation that we can do is we can permute 2 equations. And by the way, we're going to need to keep track of what these operations are and have little notations for them. So I'm going to use something as a symbol here, Pij, and that is basically going to stand for switching the ith and jth equation. Okay, so permute equation I and j. So, what do I mean by this? Well, what I'm basically saying, guys, is that, for example, in this system that we had down here, if I chose to permute the second and third equation, so I put z equals 4 here, and then I put 4y minus z equals 8 here. Right now, it's no longer in the triangular form that it was before, but I bet you would believe that we haven't really changed the linear system, right? We still have z equals 4, we still have y equals 3, we still have x equals 11/2. So if you just switch the order of your equations, you're not really fundamentally changing your linear system, and so you're not going to gain or lose any solutions to that system in the process. It's a safe operation to do. Okay, another thing that we can do is we can multiply a particular equation. Let me say it's equation I again. Multiply equation I by a constant, and I'm going to call that constant k, and k should be not 0. That's the only rule about it here. K has to be not 0. So I'm going to write that as m sub I of k. So we'll just put it in this notation here, m sub I of k. It means I'm going to multiply the ith equation by k. Again, so if we take this system in this example, you see I have z equals 4. If I multiply that equation through by 10, and now I have 10z equals 40, we're not changing the value of z when we do that. And we're not fundamentally altering this linear system at all. It's, again, another very safe thing to do. Okay, one more. There's 3 of these, as I mentioned. There's 3 of these. The third one is the most complicated one, but it's actually the one that we will use the most, which is that we can add k times equation I. So we take one of the equations, I just stands for one of the equations in my list in my system. We multiply it by k, and we add that to equation j. So we are adding a multiple of one equation to another equation. So this would be written, our notation that I'm going to adopt for this is a sub ij of k. So here we're adding k times the ith equation to the jth equation. And again, this does not fundamentally alter our linear system in any way. I want to make a note here, put a little star here, that these three operations, permuting, multiplying, or adding, these are called elementary row operations. Okay? Anybody seeing that this is a key concept in this video, because the title of the video has the letters ERO, which is the abbreviation for elementary row operations. EROs, elementary row operations. These are safe operations on a linear system that we do not gain or lose any solutions to our system when we apply them. When we're working through a series of elementary row operations, as we will soon be doing, it's going to be helpful to keep track, especially in the beginning, when we're first learning how to do these problems, keeping track of these different steps that we are taking. And so that's why these notations in the boxes are useful and important. I'm going to want everybody to kind of get on board with this and try to indicate or denote each step that they're doing with the corresponding ERO. Okay? So my second observation, no solutions to our system are gained or lost if we do EROs. Okay? And these are the EROs. The final remark, the third and final remark, is that the first two comments, the 1 and 2 above, so the remarks that we've just made, we've been talking about these remarks in the context of the equations of a linear system. But we can also just as well do the same thing with the rows of a matrix. So we can permute two rows of a matrix, we can add a multiple of one row of the matrix to another row of the matrix, or we can multiply a row of the matrix by any non-zero constant. So the 1 and 2 above apply to the rows. And what matrix is it that we're going to actually be talking about? Well, we've seen before that we generally will represent a linear system of equations with an augmented matrix. So we would write that as A sharp. Okay? So if somebody gives us a linear system of equations to solve, what we're going to do is we're going to first put it into the augmented matrix A sharp. And then we're going to take advantage of all of these three remarks. If we can get the matrix into triangular form, great. That's easy to solve by back substitution. That's the first remark we made, right? In order to do that, that's actually where we're going to use the EROs. We're going to take a matrix, an augmented matrix that maybe is not in triangular form to begin with, but we're going to apply these EROs to it to try to get it into this triangular form. Okay, so that's kind of the idea. In fact, let's write that down. I think that's an important sort of conclusion of the first part of this video today. So the process that we're going to use, here's the process, guys. This is what we're going to be practicing, right? Is we are going to use EROs to convert, hopefully convert A sharp into, now I was talking about triangular form. That first example I showed you, of course, it was a perfect triangle. It was like, you know, within a 3x3 linear system kind of thing. So it looked exactly like a triangle. It's not always going to look like a triangle. And mathematicians have sort of a more formal word to use to express this. We're not going to call it triangular form. We're going to use something that is more standard in linear algebra, which is the phrase Row-Echelon form. Okay, so it's going to be the other part of the title of this video. REFs stands for Row-Echelon forms. Okay, so we're going to use these EROs to convert our matrix into row echelon form. I have to tell you what row echelon form means formally. I'd like to give you the definition. By the way, keep these EROs somewhere close to you. I'm going to have to erase them right now, but it's going to be important that we know what they are because we're going to be using them to carry out the process that I just described a moment ago. So we'll come back and use those EROs in just a minute. But before I do that, I just want to explain what row echelon form is in case the matrix really doesn't look, or the system doesn't look like it's going to have any kind of a triangular shape to it. So let's go here and write down the definition of row echelon form. A matrix is in row echelon form if, and there really are just two parts to this definition that we have to write down. The first one is, so the first observation is that all zero rows, any rows that are all zeros are at the bottom of the matrix. So if we happen to have any rows that are just all zeros, we put them at the bottom of the matrix. So imagine though that we have a linear system where we have a row of zeros that's not the bottom row of the matrix. How could we get it to become the bottom row of the matrix? That would be the question, right? Can we do something to make that happen? Well, the process is right here, isn't it? Use EROs. Yeah. In particular, what we can do if we have a row of zeros, but it's not at the bottom of the matrix, we can permute that row of zeros. We can switch it, in other words, or interchange it with whatever row is currently at the bottom of the matrix and replace that with a row of zeros at the bottom of the matrix. Yeah, this is the idea, right? We're going to use the first ERO, the Pij, permuting, to move any rows that are all zeros. Very easy to achieve. And then secondly, this is the only other thing we need to say is that for all other rows, so any rows that are not all zeros, the first non-zero entry, and by the way, that has a name, it is called a pivot. The first non-zero entry in any other row, other than the all zero rows, this is called a pivot. First of all, it must be a 1. Now you might be asking yourself, well, what if it's not a 1? What if the first non-zero entry in a particular row is a 7, right? According to the definition, we need it to be a 1. Well, does anybody have any thoughts about how you could change that 7 or whatever that non-zero first number is in that row into a 1? Let you pause and think about it for a second, but we have the EROs again. This time, I would recommend we use the multiplication ERO, the M operation. We can take that row that starts with a 7 and multiply it by 1/7, right? 1/7 is a perfectly good constant. If we multiply a 1/7 through that row of the matrix, that 7 will become a 1. So we can certainly achieve a 1 out of it. And also, one more thing about this that's very important as a requirement. Not only does that first non-zero entry need to be a 1, it needs to occur to the right. It has to occur to the right of the pivot in the row above it. Of the pivot in the row above it. In other words, the pivots, the first non-zero entries need to be moving down and to the right, basically. Okay, so as you go down in the matrix, the pivots are going to go further to the right. Let me just draw kind of a schematic of what this looks like, just so you can kind of visualize it. So, you're going to have a 1, maybe that's a pivot. I like to circle. This is very useful. Circling your pivots or putting diamonds like I'm doing right here. After that 1, it does not matter what the rest of these numbers are. They can be anything. But in the next row, the pivot has to be somewhere further over to the right. So that means you have to have zeros. This is actually the key, right? You have to have zeros below your pivots. In the next row, the pivots would have to go even further to the right. Not every column has to have a pivot. That's okay. But those pivots do need to generally trend down and to the right. And then if we do happen to have any rows of all zeros, we stack those up at the bottom of the matrix. Those are pretty useless information. The rows of all zeros don't really matter so much. But getting these pivots arranged the way I've suggested is really the key. Okay, so we're going to use the permute operation to get the zeros to the bottom. We're going to use the multiplication operation to make those pivots equal to a 1. And it's actually the adding operation that helps us sort of move the pivots to the right as we go down in the matrix. This is really the basic idea. Okay, so let's take a minute, and we've had enough time, I think, to write down all of the background that we need for this. Let's take a minute to try an example. Okay, so here's an example. I'm going to give you a matrix A. Let's start with this following matrix. I'm not going to make it into an augmented matrix yet. I just want to take any old matrix. I'm not worrying about a linear system behind the scenes or anything like that. I just kind of want to work with these EROs and practice them for a minute. So let's suppose that this is my matrix A. And what I would like to do is find the row echelon form of A, which we can write this way, REF of A. Okay. So let's practice. This is really mostly an exercise in just using the EROs. So I'm going to start with my matrix A, and every time I do an ERO, I'm going to use this little symbol, which is a twiddle symbol, and I'm going to put the ERO that I want to use kind of above or below this little twiddle symbol. In other words, I'm about to do an elementary row operation because this matrix is not in row echelon form right now. So we have to work on it to get it into row echelon form. And by work on it, I mean we have to do these elementary row operations. So feel free to pause my video if you want to take a minute and think about it for yourself. Looking at this matrix, how could I do an ERO to it that would be useful? Remember that the pivots have to be 1s and they have to move down and to the right. That's the rule on row echelon forms. Okay. There's actually more than one correct thing that you can do here. You might be thinking to yourself, well, I have a 2 in the upper left-hand corner. And so if I wanted to, I could multiply through by 1/2 on the first row. That's one of my EROs. Totally legit to do that. You can do that. If you multiply the first row by 1/2, you'll get your pivot right here to be a 1 in the upper left-hand corner. However, there is a downside to that particular ERO in this case. If I multiply through by 1/2, do you see that I'm going to introduce fractions into the first row of the matrix right off the bat? Technically, there's nothing wrong with fractions, but I have a feeling that if we could avoid fractions and not have to do further EROs with fractional values, it would just be a whole lot cleaner for us to do, right? So is there another way to get a 1 into the upper left-hand corner that does not introduce fractions? There sure is, isn't there? Take a look. I've got 1s in the second and third row in that first column. And so if I just do a permutation, I'm going to write it as P12. That means I'm going to permute rows 1 and 2. If I just permute those 2 rows, I will get my pivot into the upper left-hand corner. Okay? What you probably are already realizing, guys, is that the choice of EROs is not unique. And in fact, the row echelon form is not unique. There can be more than one correct answer to this, which is kind of good in a way and it's kind of bad in a way. If you're trying to check your answer against a book's answer where they have just one answer in the back, you may have a correct answer that's different than one that you find in the book, because there are many correct answers for the row echelon forms here. Okay. So what we want to do is try to get a reasonable answer relatively quickly that's kind of as clean and simple as possible. So I have avoided fractions by doing P12. Now, because this pivot is right here, the pivots in the second and third row have to be down and to the right. So in other words, I actually know that I have to have a 0 here and here. Both of these have to be zeros. Let's try to get a 0. Let's do another ERO. Let's try to get a 0 into that second row. I'm not going to do anything with the first row right now. I'm just going to leave that. Obviously, it's in pretty good shape already. How can I get this 2 to turn into a 0? The best way is to add a multiple of the first row to it. And how do I know what multiple to use? Take a look at the two numbers you see here, guys. 1 and 2, right? If I multiply the first row by -2 and add that result to the second row, and you have to do this in your head, right? Take -2 times the first row and in your head add it to the second row. The key thing is you know that's going to give you a 0 right there. -2 times the first row, go all the way across the entire row and add the results to the second row. -2 times the first row added to the corresponding number below it in the second row. Okay. Now, I'm going to point something out here, guys, which is that we can actually save a little time, because I actually also know that I want to get a 0 right here. Why do I need these zeros again? It's because I don't want these to be pivots. The pivots have to be to the right. So, if these were not 0, then we would have 2 pivots on top of each other, which is not allowed in the row echelon form definition. So I know I need to make a 0 there. So you know what I'm going to do in the same step? You don't have to do it in the same step, but I'm going to save a little time by using the first row with the third row now. I'm going to see that this is a 1 and this is a 1. So at the same time, I'm going to do A13 of -1, right? That just takes -1 times the first row and adds it to the third row. -1 times the first row, it adds it to the third row. Guys, this is perfectly legitimate and reasonable to do this. 2 EROs kind of in one step, right? Just be a little careful not to abuse that too much. If you start doing like A12 of -2, and then I want to do P23, and then I want to do M2 of 4, and then I want to do P 1, 2, and you try to do too many of these things in one step, it will become too confusing, right? I especially discourage you from mixing different kinds of EROs together, right? For example, when I say here that I'm multiplying row 2 by 4, is that before or after you permuted it with the third row? In other words, I've got to make sure I'm talking about the correct row now. So this gets a little bit sloppy to do too many of these EROs in one step. Try not to do that. But something like this is perfectly safe. It's perfectly safe. I'm just adding multiples of the first row to all of the lower rows, which kind of has an independent effect on each of those lower rows. Okay, fantastic. Let's take a look at what we have here. As you might notice, the second and third row are looking pretty similar to each other. Let me just recopy the first row again. We don't really need to think about that too much. If I was wanting to, I could take a look at this 3. It's not technically a pivot yet until I multiply through by 1/3, because the pivot has to be a 1. But before I do that, I can actually already notice that if I just simply add the second row to the third row, which is just taking 1 times the second row and adding it to the third row, I'll actually wipe out the third row. Let's just do that first. So I'm going to leave the second row alone, but I'm going to use it to add it to the third row and totally wipe out the third row. Remember, all 0 rows, they're supposed to be at the bottom of the matrix, which is what we have here. And then finally, I can now, just to be technically correct, I need to make my pivot equal to a 1. I am going to introduce fractions here, but we're almost done now, right? I'm not going to have to live with those fractions for an entire string of calculations. We're basically done. So let's just multiply the second row by 1/3 now. And what we'll get is this final result. And this matrix that I'm writing down right now, my friends, this is row echelon form of A. Or let me be more precise, it is a row echelon form of A. There's lots of right answers. If we had started off at the beginning by multiplying the first row by 1/2, we would have a completely different answer at the bottom of this board than the one that we see here. The first row would have had fractions in it, right? So, and it's not that that would have been wrong, it's just that that would have been messy. It would be easier to make a computational mistake. Guys, especially as we're just first learning this is kind of, it's mostly just tedious calculations. I mean, everybody knows how to add, multiply, and permute, rows of a matrix, I think. It's not that hard. But I wouldn't do this when you're like super sleepy or it's the end of a long day, just because it is easy to make mistakes on this. I will make mistakes on this, from time to time as well. And it's really especially frustrating if you make a mistake sort of towards the beginning, and then you get all the way down to the end and everything is becoming a huge mess, or you can tell that something seems off. Then you kind of have to start all over again. So that may happen to you. It's not a reflection of your understanding of this concept or your mastery of the material here. It's just the fact that we're all human. And when I was first learning it, I also did the same thing. I made lots of little errors, and hopefully some of these tricks, like trying to avoid fractions and trying to keep your work clean, not combine too many steps, that stuff can really, really be helpful. I do want to make one final note here, guys, on this video, and then we will call it good. I just mentioned that the row echelon form of A is not unique. In other words, there is not just one right answer. Yeah, there can be lots of right answers. However, there is one thing about every correct row echelon form that is shared in common. Namely, every correct row echelon form of A contains the same. So they share something in common. You can pause the video if you want to try and think of it for yourself. There is one thing about this that all row echelon forms share in common, namely that they will have the same number of pivots. Aha! They have the same number of pivots, and that quantity is so important. It's a big, big concept in linear algebra, so it's actually something, I'm going to write it as a definition. The number of pivots in any row echelon form of a matrix. So you take any matrix and you do EROs on it by whatever means you want. You bring it into the row echelon form with all the pivots going down and to the right, the rows of zeros all at the bottom. You do all of that stuff. The number of pivots in any row echelon form is called the rank of the matrix A. This is a very, very important idea. We're going to see this concept for a long time to come. The rank of a matrix, it's the number of pivots in any correct row echelon form for a matrix. So if you come up with a row echelon form and you check it with a friend and they have a row echelon form that's different than yours, the one thing you do know is that they had better have the same number of pivots. They better have the same rank, okay? So in our example above, the rank of that matrix, I don't care how you do the EROs, 30 different people can get 30 different row echelon forms that are all correct, but the one thing that they will all have in common is the number of pivots at the end of the day. And you can see here that we have 2 of them. And so that, therefore, is the rank of the matrix. The rank is 2. Okay, well, guys, these are just some of the mechanical tools, these elementary row operations, right, that we're going to need to actually solve linear systems. So in this video, we still haven't quite taken a linear system and tried to solve it yet, except for that first one that I did by back substitution. But next, once we are good masters of how to use elementary row operations to bring a matrix into row echelon form, once we've kind of got that down, we are fully equipped to then use those tools to solve linear systems. And so that is certainly what we're going to be doing next. I hope that this video has made some good sense. If you've got questions about it, be sure to jot them down, send them to me. Be happy to help you out, answer them. And just take your time practicing using EROs to bring a matrix into row echelon form. It's not a super advanced technical topic. It's just a little bit tedious, and you do have to be careful, as you can probably guess. Thanks so much, guys, for watching this video today. I appreciate it, and I look forward to seeing you all again very soon. Bye for now.